All righty. All right, let's finish up our electron configuration notes. So we're going to look at some exceptions to electron configuration, and then we're going to look at how the ions electron configuration is. So sublevels are most stable when they are either half or completely filled. So electrons will shift to different energy levels or sublevels to accommodate for this stability. And so that makes there some exceptions to some different elements from what we think the electron configuration to be should be into what it actually is. So there's 4 of them. And I mean, these are just things you just have to memorize. So the first one is chromium. And if we expect it to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. That's where we would expect it to be. But this right here is very unstable. Kind of like a half-filled valence electron shell. And so what happens, one of these electrons from the energy level 4s jumps over there into the 3d. And then by doing that, both of them end up being half filled and it's more stable. So the actual is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So now both are half filled. And the other exceptions, you know, kind of end up being very similar when we look at those. So our next one that we're going to look at is copper, which is element number 29. So first of all, we'll start off, we'll look at the expected, what we think it should be. So 1s2, copper's in the same period, in the same D as chromium. 2s2, 2p6, 3s2, 3p6, 4s2, 3d9 is what we think it should be. But once again, this is unstable. It's kind of like the halogens when they need 8 valence electrons and they have 7. So same thing's going to happen. One of these electrons is going to move over to fill that out and make it more stable. So then you actually have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So then that D is completely filled and the S is half filled. So that makes it more stable. All right, I'm going to erase this so y'all can see. All right, and then our next one, there's a couple more. Next one we're going to look at is silver, which is number 47. So if we do the expected first, and I'm going to shorten it by just doing the noble gas. So krypton, 5s2, 4d9. So just similar to what we did with copper. One of these is going to jump over and fill that out. So we end up with an actual of 5s1, 4d10. And then the last one we're going to look at is molybdenum, which is MO, element number 42. And we'll do the same thing, what we think it should be by looking at it. We think it should be a, let's see, it's, oh, no, what happened? Krypton, and then 5s2, 4d4. So same thing, if this one jumps over here, then we end up with 2 half filled, which will be more stable. So actually, we have a 5s1, 4d5 is how the electrons exist. And remember, we're talking about electrons and where they exist, but like it's not like some big defined line. Okay, these are 3D areas that have to do with the energy and the frequency. And sometimes those electrons may move out of that area, but this is where they have the highest probability of existing. All right, so if you're doing your practice, you may come across one of these here or there. And so if you think that the key may be wrong, which believe me, I do make mistakes. So there will be times that the key is wrong, but just double check that it isn't one of these exceptions. It may be that, and that's why the key may look a little different or seem like it's wrong. All right, the next thing that we're going to look at is ions real quick. So we know ions either gain or lose electrons to become more stable, and they gain them or lose them to their valence shell. So cations lose electrons from the outermost S and P. We talked about that yesterday, that the valence electrons exist in the highest energy level, S and P. And then anions are nonmetals. They're going to gain electrons into the outermost S and P. So the reason the ions they're doing this is because they are trying to become more stable, or they become more stable. So they are trying, or I don't know, that makes it actually sound like they have a wheel. I don't think they think I'm going to try to do this, but anyway, they're trying to be isoelectric. New vocabulary word. Isoelectric with a noble gas. And isoelectric means same electron configuration. So we know the noble gases are stable, so they're just by gaining or losing, they're trying to get that stability. All right, so we'll look at oxygen versus oxide first, which is the oxygen ion after it's gained 2 electrons. So it's an anion. So if we look at oxygen and its electron configuration, it is 1s, 2s, and then on the 2p, it has 4 electrons. So it has those 2 open areas on the sublevel. So when it goes from this to become an ion, it gains electrons into those 2 areas. It usually does that probably by combining with a group 2 metal. So then if we look at our oxide ion, then it would now be filled up. Outermost energy level is 2 S and P, because it gained 2 electrons, are now completely full, and it has its complete valence. Does not want to write. And so we would say it is isoelectric with neon. I can rewrite that up here. Isoelectric with neon when it's the ion. Because if you look at your periodic table, Oxygen is element number 8. So if it gains 2 electrons, it's going to move over 2 boxes. So now it's going to have the configuration of neon. And then the same thing when we look at our metals, except instead of gaining electrons, they're going to lose electrons. So we'll look at one of those. So we'll look at calcium versus the, oops, not that versus the calcium ion, which is the Ca2+. It has 2 valence electrons and it's going to lose those 2 valence electrons. So just the calcium itself is 1s, 2s, 2p. It's on the calcium's on the what 4th period. So we got a little way to go. 3s, 3p. And finally we get to its valence electrons because 4th energy level is the highest energy level. And it has 2 electrons in that 4s. So that's what's making it so unstable, very close away from the 8 valence. So it's going to lose these 2 electrons. And when it does, the electrons are now, the highest electrons are now located in a energy level 3. And you can see 2, 4, 6, 8. So there's a valence of those. You have the whole 8. So that's much more stable. Remember, the 4s is just an area in space with a different energy. So it's not like you lose a piece of the atom. It's just that they're not going to exist in that higher energy level. So now my calcium ion, as you can imagine, is pretty much the same thing. Got my 3s, so that is now a valence, a couple of valence electrons, and then my 3p makes up my other 6 valence electrons. So what would calcium be isoelectric with? Not that I can even get my pen to write that. Argon, exactly. It's going to be isoelectric. With argon, because it had 20 electrons, it lost 2, so that means it has 18. So now it would have the notation of an argon, so we would say it was isoelectric with that. And then there are, in your practice, there's some ions, so you'll get a chance to practice some of those. All right, I think we got maybe about 8 minutes or so, so you got a little bit of time to look at some practice and get ahead for your quiz on Monday. And I'm going to stop taking.